to the next speaker, who is Martina Busetto from Politecnico di Milano. Hi, Martina.
Yes, good morning.
So Martina will talk about a virtual element approximation for immiscible, incompressible two-phase flows in porous media. Please, the stage is yours.
Thank you. Thank you for introduction, and I hope you can see the slide.
Yes.
Okay, thank you. So first of all, I want to thank the organizer for giving me the opportunity to talk in this conference. So today I will present the research that we are doing on a virtual element approximation for immiscible, incompressible two-phase flows in porous media. So this work is in the general framework of the virtual element method. So as we have seen, this method is a recent extension of the finite element method that allows to solve a partial differential equation on general polygonal meshes. And this is the reason why this method has become very attractive for solving problems characterized by complex geometries. However, the literature for nonlinear problem is still relatively youth, and in particular, there are still very few applications to complex and realistic geological flow model related to porous media. The aim of our research was to try to investigate a primal C0 conforming virtual element formulation for the two-phase flows equation of immiscible fluids in porous media. These equations are particularly challenging because they are time-dependent, coupled, and nonlinear. And in particular, we wanted to numerically investigate the performance of the fully discrete schemes, both in terms of mesh flexibility and the simplified construction of high regularity and high order approximation. These equations are interesting because they find application in different fields, ranging from chemical to petroleum engineering, from nuclear waste disposal safety to hydrology. Before stating the governing differential equation, I want to give an hint on the physics behind the problem. So we are dealing with a porous medium that can be seen as a porous matrix plus some void space. And since we are dealing with two-phase immiscible flow, this means that the void space is completely filled by two immiscible fluids that are denoted as the wetting phase and the non-wetting phase. For what concerns the mathematical model, we need to introduce a space-time domain that I will denote with Qt. And then we needed to choose a suitable formulation of the problem. In literature, there exists a different formulation, and we have selected the pressure saturation formulation. The assumption of the model are incompressibility of the fluids and time independence of the porosity of the porous medium. And in this particular formulation, there are two primary variables that are the saturation of the wetting phase, that is denoted by SW, and the pressure of the non-wetting phase denoted by Pn. In systems of equation number 1, you can see the equation of the pressure saturation formulation. So this system mainly consists of two equations plus the boundary condition and the initial condition for the saturation. The equation in red is called the pressure equation, and it is elliptic with respect to the pressure of the non-wetting phase, whereas the equation in green is called the saturation equation, and with respect to the saturation of the wetting phase, it could be either nonlinear hyperbolic if the capillary pressure Pc is equal 0, which means that this term goes away, or it could be parabolic if the capillary pressure is different from 0. In the parabolic case, it could be either diffusion dominated or convection dominated. As you can see in these two equations, there are different coefficients. In particular, I want to underline that the mobilities that are denoted as lambda, lambda w, and lambda n, and the capillary pressure denoted by Pc are function of the saturation of the wetting phase, And since we want to retain the physics behind the problem, we have adopted the Brook and Corey empirical model in order to model the dependency of the mobilities and the capillary pressure on the saturation. And so in general, this will be nonlinear function of the saturation. And finally, I want to underline that the derivative of the capillary pressure with respect to the saturation is negative, so that this diffusive term is indeed a stabilizing diffusive term. So these equations are time-dependent, nonlinear, and coupled. And this, of course, poses several difficulties from the point of view of the numerical treatment. And this is the reason why different techniques have developed in literature. So the traditional approach involves either the use of a field-implicit method or the use of an operator splitting technique. And they are usually coupled with the traditional space discretization scheme. In our approach, we used an iterative operator splitting technique known as IMPIS, plus a virtual element method. So more precisely, given the time interval, we discretized it and we consider a subinterval between Tn and Tn plus 1. Then we apply the Crank-Nicholson scheme to the systems of equation number 1, and this gives rise to a full implicit systems of unknowns, the saturation and the pressure at the time instant Tn plus 1. Then we linearize the saturation equation with respect to the saturation at the time instant Tn plus 1 using a Newton-Raphson method. And then we decouple the two equations adopting an iterative IMPIS formulation. So at each Newton iteration kth, firstly, the saturation equation provides the saturation at the time instant Tn plus 1, Newton iteration kth plus 1, and then the pressure equation provides the pressure at the time instant Tn plus 1, Newton iteration kth plus 1. And as a space discretization scheme, we use the virtual element method. In this presentation, I want to mainly focus on the space discretization through the use of VEM. So we used an enhanced C0 conforming virtual element space, allowing the possibility of using different order for the pressure and the saturation. So given the domain omega, as usual, we introduce the tessellation made of general polygons E, and we define the classical local virtual element space for order k greater or equal than 1. So here you can find the classical definition of the enhanced C0 conforming virtual element space. And then we introduced the projection operators. Again, here there are the classical definition of the projection operator, and in particular we needed the H1 projection operator denoted with pinabla k, the L2 orthogonal projection operator denoted with pi 0k, and finally the L2 orthogonal projection operator of the derivative denoted by P0k minus 1 of the gradient. As I pointed out before, in the equation there are quite a lot nonlinear coefficients, and in general they are non-polynomial functions. So we decided to evaluate them using the element-wise polynomial projection. So now, as we have seen in the two equations, there are different terms. And so I decided to focus on the most interesting one from the point of view of the virtual element method. So for what concerns the pressure equation, I will focus on the diffusive term that is associated to a local form that I denoted with A. And so according to the classical VEM theory, we know that this form must satisfy polynomial consistency and stability. So for what concerns stability, we use the classical definition, whereas for the polynomial consistency, we have to slightly modify the requirement because in this expression, you can see that we evaluate lambda, the mobility, on the local polynomial projection pi 0k of the virtual element function. So as usual, we define the diffusive term as the summation of two terms. The first one that guarantee polynomial consistency according to the definition above, and the second one that guarantee the stability. For the stabilizing form, we have used the Pinabla K projection. For what concerns the saturation equation, I will focus on the reactive term and the diffusive term denoted by the local form C and D. So for the reactive term, we adopted the usual definition of polynomial consistency and stability. Whereas for the diffusive term, we have to slightly modify the requirement for polynomial consistency, as we did for the diffusive term of the pressure equation. And so you can notice that for the mobility lambda W and the derivative of the capillary pressure, we evaluate them in the local polynomial projection pi 0k of the virtual element function. So we defined the local virtual element form as, again, the summation of two terms. So the first terms, as we saw before, guarantee the polynomial consistency according to the definition that I gave before, and the second one guarantee the stability. For the reactive term, we have used in the stabilization the pi 0k operator, whereas for the diffusive term, we have used the Pinabla K operator. So we have implemented this code numerically in C++, and then we have tested the method. So first of all, we have performed a convergence analysis for a case in which the analytical solution is known. And in particular, we have considered the non-degenerate case in which the systems of equation number 1 is a system of parabolic nature of coupled nonlinear equation. So we have evaluated the spatial discretization error at the end of the time interval, considering both the H1 norm and the L2 norm. So provided that the time integrator error is sufficiently small, we expected the typical order of convergence of the parabolic problem. So we considered a space domain, which consists of a square, and a time domain between 0 and 1. We considered the following analytical solution. Of course, this solution have no physical meaning, but we try to retain the physics in the definition of the order of magnitude of the pressure, and on the fact that the saturation ranges between 0 and 1 in the considered space-time domain. And moreover, we adopted the physical data for the porous medium and the two fluids. So we studied the convergence considering 4 different meshes. The first one made of triangles, then squares, polygons, and finally an agglomerated mesh. For each one of these 4 different types of meshes, we considered 4 different refinements. And so in the bottom part, you can see the order of convergence with respect to the number of elements of the mesh. In particular, in the left-hand side, I have reported the result for Vem order k equal to 1, whereas in the right-hand side, I have reported the result for Vem order k equal to 3, for both the pressure and the saturation. In the lower part of this graph, you can see the L2 norm study, where in the upper part, the study of the convergence in the H1 norm. So you can see that the slope of the dotted line that represent the numerical error are quite similar to the slope of the expected slope, theoretical slope, that is represented by the triangle. Then we considered some benchmark problems, in particular the McWhorter and Tsunada problem, that has a quasi-analytical solution. This problem is for the case in which the capillary pressure is different from 0, so we are in the parabolic case. And this represents a simplified version of a model of a reservoir. The reservoir is represented as a one-dimensional horizontal porous medium. And the oil that represents the non-wetting fluid is horizontally displaced by the water that represents the wetting phase. And the water is pumped inside the domain at the left-hand side. The original problem is monodimensional, but since we need to verify a code on a bidimensional domain, we consider the solution to be constant along the y direction. We consider two different test cases. So test case number 1, which is called the bidirectional flow, and it is diffusion dominated. So first of all, we verify that by refining the mesh, the error decreases. In particular, here I put the plot for the L2 error. And for Vam order k equal to 1, and we considered 4 different type of meshes that are similar to the one that I showed you before. Then here I show a qualitative comparison between the quasi-analytical solution on the left-hand side and the numerical solution on the right-hand side. So this simulation is for a polygonal grids, and for Vam order k equal to 1, and this represents the solution at the end of the considered time interval. So in the upper part, there is the comparison for the saturation, and in the lower part, the comparison for the pressure. Then the second test case is the unidirectional flow. In this case, we can go from a diffusion-dominated case to a convection-dominated problem. This is possible just by varying the values of the saturation at the left inlet. In particular, in the upper part, we can see that we have selected a values of the saturation at the left inlet, which is denoted as SW0 of 0.6. So you can see here the value. And this is a diffusion-dominated case. Then we have increased the values of SW0 to 0.9. And so in the lower part, you can see a case that starts to be convection dominated. So in figure 4D, you can see that in the numerical solution, some oscillation started to appear. And so we tried to see if it was possible to stabilize the solution, mitigating the spurious oscillation. So we introduced a nonlinear stabilization term, which involve a localized nonlinear artificial viscosity, which depends on the saturation. The dependency of the artificial viscosity on the saturation was modeled through a modified version of the nodal gradient jump viscosity approach. In this approach, the viscosity is related to the local jump and the mean values of the gradient of the saturation. So applying this nonlinear stabilization, we found the solution that we can see in figure 5. So you can see that this nonlinear stabilization seems to be able to mitigate the spurious oscillation in case of sufficiently refined mesh and Vam order k equal to 1. And so you can compare this figure 5 with the figure 4D that we saw before. So in conclusion, I want to point out that in this presentation, I focus on these benchmark problems because for this problem, we have a quasi-analytical solution. And so we can compare qualitatively and quantitatively our numerical solution with a quasi-analytical solution, but the method that we have developed can be applied also to more complicated problems. And so finally, I thank you all for your attention.
Thank you very much.